All right, we're going to look at some final thoughts on solubility and equilibrium. And so factors affecting solubility are a couple of these we've already kind of talked about. So the common ion effect, you have an ion that's coming from another source that is in common with the insoluble solid ions that are present, then that's going to limit solubility or lower solubility. And that, again, goes back to what we've talked about with Le Chatelier's principle, that if I, for example, is barium sulfate solid, if I have a source of barium ions coming from another substance, then that's going to, an increase in a product concentration will drive equilibrium to form more reactants. And that's because, again, at equilibrium, there's only a certain concentration of barium times concentration of sulfate that can be present. So obviously, if one of those concentration goes up, the reaction has to use up and lower that concentration. So that reduces solubility then. So common ion effect in that case is going to reduce solubility for the solid salt. Other things, we just got done talking about pH, so looking at the effect of, basically it has to do with the identity of the ions in the insoluble solid. We've already seen with like a basic anion, so like if hydroxide is present, lowering pH is going to allow that to dissolve more because you've got a side acid-base reaction between the hydrogen ion and the hydroxide ion. So that's essentially like removing the hydroxide ion from solution with the acid via neutralization. And then that allows for more of the solid to dissolve then because it's lowering that hydroxide concentration. The other thing that we have that can happen is, as we've talked about, the hydrolysis of ions from weak conjugate acids or base. Kind of a similar idea here. We see depicted is like if I have this, lead 2 fluoride, and the fluoride ion we can trace back to being a conjugate weak base from the weak acid, hydrofluoric acid. That if I have an excess of H plus present in solution, that is going to start this side reaction with the fluoride ion, and as a result, it's producing HF molecules, but that is also lowering the fluoride ion concentration. So the fluoride ion concentration is decreasing because of this side reaction that then allows for more of the lead fluoride to dissolve to kind of replenish the concentration of fluoride that's been lost. So you end up with more of the lead dissolved. And again, the fluoride is being tied up, so it's not, we're not seeing a huge increase in the fluoride ion concentration because that's being tied up as HF, but we will see more of the solid dissolve. You're not going to see that happen with the anion from that we associate as a conjugate base from a strong acid. So like in the example here, the lead 2 iodide, the iodide ion we trace back to the strong acid, hydroiodic acid, and we know that the conjugate of a strong acid is very, very weak and is not able to pick up H plus in the same way that the weak base conjugate would. So we don't see any effect on solubility by the decreasing pH for a solid that involves a anion from a strong acid, but we do see a increase in solubility when the pH is lowered for something that does have a basic anion. The opposite is true then with acidic cations. So the acidic cations that we associate with, hydrolyzing to form acidic solutions, those will be more soluble in basic solutions. So kind of the same idea, just in reverse. Just to take a look at that effect on solubility, let's look over at a calculation real quick. Actually, sorry, first we'll look at a qualitative question and then a calculation. So which of the following salts will be substantially more soluble in acidic solution than in pure water? So that means if we're adding additional H+. So criteria is we're looking for, if it's acidic, we're looking for an anion that is can be traced back to a weak acid, right? So it's the conjugate of a weak acid. So carbonate we associate with carbonic acid. That is going to be a weak conjugate base. So this we would expect to have an increased solubility in a lower pH. Same thing with the sulfide ion. We can trace that back to H2S, which is a very weak acid. Iodide, so that we would trace back to hydroiodic acid. That's strong, so this we would not expect to improve solubility in low pH. The cyanide ion, again, we can associate with the weak acid HCN, so that should be more soluble in a lower pH solution. And then phosphate, we can trace back to the phosphoric acid, and that also would then have a greater solubility in a lower pH. Now, if we were asked to calculate the solubility, so obviously we've talked about before, if I just have the KSP, so like here's manganese hydroxide, if I just have the KSP, I could, figure out what these concentrations are. So this would be X, this is 2X, solve for X, that's your solubility of your solid since it's 1-to-1. But if we're told like the pH is buffered to a certain, that the solution is buffered to a certain pH, then that means that we have to figure out what that does for these concentrations. So if you're told that you have a certain pH, remember that pH we trace back to hydrogen ion concentration. So pH of 7 is 1 times 10 to the negative 7th, right? 10 to the negative log of 7 is 1 times 10 to the negative 7th molar. We also know that we can relate that to the hydroxide ion concentration. So Kw equals H plus times hydroxide, or again, you could find the POH, however you want to do it. That also means then that our hydroxide ion concentration for this scenario is the same exact thing as the H plus. So however you decide to find hydroxide, the pH gives you H plus, and then from there you figure out what hydroxide is via those relationships. So this is the case. So this then kind of looks very like one of those common ion problems we've done before, where I have the hydroxide ion concentration here. So I would plug that in here. And again, we know that there's going to be the other ion to solve for. So, and the fact that if we're looking for solubility, that's ultimately the question. The amount of manganese ions that end up in solution, since it's 1-to-1 with the compound, that is going to be the molar solubility, and then we can convert that to the solubility in terms of grams. So plugging in the numbers to the expression, so figuring out, again, if this concentration is 1 times 10 to the negative 7th, that is squared. Make sure you use the equation, write it out so you can use it. So that's squared. Looking for the manganese concentration, you end up getting 16 molar. So again, stop and crunch the numbers. And so if it's 16 molar, that's, again, moles per liter, and just converting the moles to grams. And this is the molar mass for manganese hydroxide, and you end up with 1.4 times 10 to the third grams per liter. So that's pretty soluble. And again, if you look back at how low this solubility is, it's lowering this pH is then resulting in more of the manganese to be able to get into solution, because more of the manganese hydroxide is dissolving. So that is the effect of pH and other things. So another thing that can be formed that affects the concentration of the ions and therefore the solubility of the salt is the formation of complex ions. So, we worked with complex ions in our equilibrium lab with iron thiocyanate, and essentially all that is it's a complex ion. So it's a charged group. It's usually it's a Lewis base that is then sticking to positive ions, and as a result, because it's not always a positive ion overall, but the group is charged overall, so that's why it's still an ion, but it's complex because it's not just a single, it's not as simple as even other polyatomic ions we've seen. So just to go back, a Lewis base, we should recognize the name Lewis from like the Lewis structures and Lewis dot diagrams. So when you think Lewis, I would think electrons, and what a Lewis base means is it's something that has a lone pair of electrons to contribute to something else. The Lewis acid is something that can take in a lone pair or will stick to a lone pair of electrons. So, thinking about these cations are sticking to like the ammonia ion or the cyanide ion and so forth. So a complex ion has a formation constant, and so you can see what the equation basically, if this is made of a silver and two ammonias, then that's pretty much what the equilibrium equation is that this formation refers to. The higher the constant, that means the more stable the ion is. The other thing too you'll notice is these constants are gigantic in comparison to the constants that we've been seeing so far in our equilibrium unit. So that would imply that these are pretty much completion reactions. So you should kind of treat these as, like, if I have silver available and the ammonia is available, they're pretty much going to react and form as much, based on stoichiometry, will form as much of the complex ion as is possible based on stoichiometry. So anyway, that would be, if you need to deal with a reaction involving complex ions, again, what's happening is, so if we have like silver chloride, for example, is an insoluble solid. We have a little bit of silver ions, a little bit of chloride ions, but it's essentially a side reaction. So if silver, the silver complex ions being formed, that's taking the loose, free silver ions out of solution, and then is allowing, again, if you're looking at, plugging that value into the equilibrium constant expression for the silver chloride solubility, silver ion concentrations essentially not there anymore because this is formed and taken up those silver ions. So it allows for the reaction, the silver ion, silver chloride solid to dissolve even more. So for this, and also for the calculation involving the pH, if you have to figure out which way the solubility is going, you can kind of think about this as like removing the silver ion concentration, or, we talked about the, the hydrogen, removing the, the anion concentration. But if you needed actual equilibrium constants for these reactions, remember you can add together reactions or add together equilibrium systems and then also multiply their constants, and that can give you a constant for, like, for this, for this equation that we see down here. You would add together the KSP reaction for the silver chloride and also for the formation of the complex ion equation, and then combine the constants and you get the constant for this. So keep that in mind if you're ever posed with a calculation problem involving this. There are some some solids that can behave and be more soluble in either a lowered pH or a higher pH. And so there's some examples there, and that would just be, there's the anion is available to react with the acid, or in this case we see the complex ion forming, which is allowing it to dissolve in basic as well. I wouldn't worry about memorizing these, who does what and which complex ions are formed. It's more if you're given the information about them, then you can make your explanation of, this formation of this ion removes this ion and therefore, shifts equilibrium. That type of explanation is more what we'd be, needing to worry about off the top of your head, rather than, figuring out, like, knowing. I don't expect you to know that, that this complex ion forms or anything like that. One last thing is precipitation. So selective precipitation and trying to separate a mixture or analyze a mixture and figure out what's in there via forcing various precipitations to occur. And we already looked at this a little bit when we did equilibrium in the first place. Essentially, you're just comparing the current concentrations to the equilibrium constant for the solubility. So, like if I'm trying to precipitate something out, something with a lower equilibrium constant, lower KSP, is going to precipitate. It's going to require a lower concentration to be present for that to precipitate first, and so forth. You can also see here from the chart, this is heavily based in the solubility rules, which we don't have to have memorized anymore, but nonetheless you can kind of see the, the adding of the HCl. Well, that chloride ion is going to precipitate certain ions and let other ones pass through. And then over here we've got the, adding of the something containing the sulfide ion, which then again would precipitate some of these sulfide ions, sulfide compounds, which again we could differentiate based on their solubilities. So, the lower solubility constants will precipitate first. And that's the last problem that I'm going to have us take a look at here, is involving this selective precipitation. So first off, just a qualitative example. And this is, consider a beaker containing a saturated solution of lead iodide at equilibrium, and so we've got the picture. And if the solid potassium iodide is added, will the amount of solid lead iodide at the bottom of the beaker increase, decrease, or remain the same? So if you think about that, at equilibrium, we've got a certain concentration of lead and iodide, and their concentrations, their product equals this. So adding this, dissolving, again, the potassium containing compound is going to be totally soluble. So that's going to increase our iodide ion concentration. So if this number goes up, our product amount goes up, that will shift us back and form more of the undissolved solid. So this, in fact, should increase the amount of solid at the bottom of the beaker. If that's what's happening, then that also means if we're shifting left, that we're going to be using up the lead ions and the iodide ions in that process in order to reform some of the solid. So the lead concentration will be decreasing. So that's what part B here is asking us about. And lastly, for C, will the concentration of iodide ions in solution increase or decrease? I don't particularly care for the phrasing of this question, but so when we add the potassium iodide, the iodide goes up. So that portion, if this is referring to, once the shifting starts, then we're going to start seeing the iodide decreasing along with the lead, because again, the system is trying to re-establish equilibrium. So initially, when the iodide's added, yes, it goes up. But then again, as the system tries to re-establish equilibrium, we'll see it starting to go down again. And if we wanted to look at the selective precipitation from the calculation standpoint, we could look at a problem like this. If you want to take a look and read the problem, pause it if you must. So we have a solution that already has these two concentrations in it, and then we're adding iodide ions slowly, and the KSPs are given for for lead iodide and for copper iodide, and we're trying to figure out which one's going to precipitate first and which concentration, what concentration of iodide we're going to need to begin precipitation. So first, writing out your equations. That would be my first step. So there's the lead iodide. Get these all on the same page. And there's the copper iodide. And don't forget that this term is squared, so that's pretty important. And so the idea is that, I would suspect with this copper iodide, since the KSP is smaller, that we're going to see that precipitate first. Because there's this squaring in the term here in the lead iodide, I wouldn't be quick to totally jump to that as an answer, but I would kind of lean towards the lower KSP to be suspicious towards that. If they have the same ion amounts, then that would definitely be precipitating first for sure. But we can check out the numbers. So again, this is, I'm going to kind of look at each of these scenarios one at a time and plug in. I think I did the copper one first, but so starting concentration, there we go. And so for copper to precipitate, for copper iodide to precipitate, then I'm plugging in. So this is the KSP equals copper times iodide concentration, and then I'm solving for the unknown. So this iodide concentration would have to be 5.3 times 10 to the -8th molar for precipitation to start. So that's where the these amounts would equal the constant. So anything this or above is where the copper iodide would precipitate. If I do the same thing with the lead numbers, then this is what you get. So there's the KSP, there's the copper, and the iodide is squared. So make sure that you factor that in with your math when you divide these two, square root, and you get this. So this is a much higher concentration than what we got up here. So at this concentration, 5.3 times 10 to the -8th molar, that's where we would start to see the copper iodide precipitating. And then once all of the copper was removed from solution, then you would start to see the lead starting to precipitate out. And that is that.